Okay. So welcome everybody to today's seminar. We have today the pleasure to have with us Dr. Angel Sanz from the University of Madrid. The seminar is the line of research of the Bohmian quantum mechanics, as you know. And Thanasis will make an introduction and then the speaker will continue. So, thank you again.
So, thank you everyone. Here we have, today we are honored to have Dr. Professor Angel Sanz from the Department of Optics from the University of Madrid. He's a leading expert in Bohmian quantum mechanics with many talks and papers in the field. First time that I met him was back in 2013 when I was a PhD student. And I met him in Rome in an Eastern school for open quantum systems. So he's well known in the field, and he's a friend of Christos Ευθυμιόπουλος, and we are delighted to have him today with us. So, Angel, if you are ready, we can start.
I'm ready, Demos.
Perfect.
So, thank you very much for the kind invitation. I mean, for me, it is a true pleasure to be invited to the Academy of Athens because of these connotations that this place have for the Western world, you know. So, in this sense, when you invited me to deliver a talk there, I thought that I wanted to present something in between, not philosophy, but somehow thinking, no, the ideas joined to the applications. So the title, "Can we learn anything new about the quantum world from Bohmian mechanics?" is intended to stir minds, because as you know, because you also work in this field, there are still people skeptical about quantum mechanics. They think that this is kind of weird or exotic interpretation of quantum mechanics, although it is as valid as any other picture of quantum mechanics. So I have divided the talk with this idea in kind of two parts. One that goes more to the conceptual level. Okay, we are going to talk about whether there are, paradoxes are really intrinsic and necessary in quantum mechanics. We are going to see whether trajectories are truly forbidden in quantum mechanics, because this is a kind of mantra that we hear since we study in the university. Okay, and we are going to see some examples from the literature that point that there is a need actually for this. In the second part, I will focus on some applications. Okay, in particular, just this kind of important and paradigmatic systems, such as the two-slit, the two-slit with entangled particles, and then something that I have called post-Bohmian mechanics, that is applications of Bohmian mechanics to other fields, in particular to the field of optics, where which I am developing at this moment. So let's start. I have to clarify that I'm not a historian of science, I'm not a philosopher of science myself, and mainly I'm not a Bohmian in the sense that that you may know. I say that I'm not a Bohmian in the sense that this is not like an orthodox view of the quantum world. I like to be always very flexible. Now, yet, leaving all these specifications aside, one thinks, in the end of the day, what can we do to understand quantum physics? No? So my idea here is just, let's play Bohr observables or Bohm statistics. Okay, they are very tightly connected, but doing Bohm. Okay, are the trajectories forbidden? Let's see. When we go into quantum mechanics, well, this is one of the very first things that we found. There is a reality somewhere, and we can either know one part or another, but we cannot know anything about the whole thing. So the same happens with Bohmian mechanics, and this is the very main idea that I want to convey in the talk, okay? That we never leave this view, okay? We have, for instance, whether there are waves or particles. It depends on which model better fits our needs at every moment. We talk about cats that are alive or they are dead. No, we represent this by means of a state function. Now, do these have any reality? I mean, we can construct a Schrödinger cat in the laboratory with atoms, with molecules, but are they in a superposition? Are they truly in superposition? Let's see. For me, all of this, just getting back to the place where we are, the Academy of Athens, this takes me back to Plato's myth of the cavern, where the slaves, somewhere here, they can see the shadows cast on the wall by some people who is hidden behind the wall. So with quantum mechanics, it seems that everything works in a pretty similar way. We will never know what the reality is, what the reality of quantum particle is. But we can obtain descriptions of those particles. These are our shadows. Well, actually, there is no need to talk about waves or particles. We could have even both at the same time. We could actually leave particles for classical-like theories like Newtonian mechanics, for instance. I don't say Hamiltonian mechanics because being classical mechanics, it is based on a different concept. It is based on the concept of surface of action. It is not based on the concept of point-like and actions at a distance. This is something very, very, very interesting because in quantum mechanics, this was actually the idea that David Bohm tried to convey to the people with his seminal works from dating back to 1952. He wanted to determine whether it was true that there is only a unique description of quantum systems. You know that the von Neumann theorem stated in 1932, if my memory doesn't fail, it says that, well, if you want a theory based on what they are called hidden variables, the extra variables that would explain the weird behaviors that we observe in quantum mechanics, this implies that we should either this additional model is wrong, or if it is true, it should invalidate quantum mechanics. Of course, this theorem was based on the idea of locality, Einstein's locality. What happens here is only influenced by a neighborhood around it. It can never be influenced by something that is farther away. What David Bohm said is that no, this is actually possible, but in order to do so, we need to include the concept of non-locality, a concept that later on John Bell would exploit and that has given rise to the modern quantum technologies that we have now. Okay. Now, David Bohm's idea was very simple. One starts from a Schrödinger's equation. We consider, instead of a complex field variable, we consider two real field variables. These are the amplitude of the complex field and the phase of this complex field. If we introduce this ansatz into a Schrödinger's equation, okay, without making any sort of approximation, we obtain two equations here, two equations of motion. One for R squared. R squared is actually the probability density. This is the continuity equation, where this term here is identified with the quantum flux or quantum probability current. Okay, and another equation of motion related to the phase. This equation of motion, as you can see here, is very, very similar if we neglect this term, this last term, to Hamilton's equation. Well, what Bohm proved with this manner to write Strange's equation is actually that we can obtain some kind of corrections to Hamiltonian mechanics, or the other way around. If we consider h bar going to 0, we can say that Hamilton's approach to classical mechanics is just the limit of h bar going to 0 of quantum mechanics. This is why I said before that we cannot put on the same level classical mechanics and Hamiltonian mechanics, because they are quite different. Now, further elaborating Bohm's model, he proposed, or he postulated, that if we have this sort of quantum Hamilton-Jacobi equation, there should be a term, v, velocity, related to the gradient of s, in the same way that we have the Jacobi law in classical mechanics. He introduced this as a need. Okay, I need a postulate, I need to introduce these velocities. Well, if I have velocities, I can integrate it in time, and if I do so, I will get trajectories. And what are these trajectories? Well, these trajectories can be identified with the trajectories followed by quantum particles. We're going to see that this is not totally true. Now, before David Bohm published his paper about 25 years earlier, Louis de Broglie proposed that a model in which he already inferred some of the ideas that Bohm would later publish, as it is that there are waves, and on top of that waves, the particle is a kind of singularity that is guided by this wave. This is what is commonly called or denoted as the pilot wave theory. By the same time, Madelung also proposed a reformulation of all the quantum stuff or quantum mechanics based on Schrodinger's equation as a hydrodynamical model. He found exactly the same equations as David Bohm found 25 years later. Exactly the same. So, with this, we find that the obscure view provided by Schrodinger's equation can be somehow clarified, or at least rendered some light by these pictures. In one, Bohm's picture, we have that the physical system contains or consists of two elements, two indispensable elements: a wave, which follows Schrodinger's equation, and a particle follows this simple equation of motion. We don't need actually these two equations. With only these two equations, we can reproduce all the results of quantum mechanics, at least in the non-relativistic term. In the last year, some relativistic models have been proposed, nonetheless. Okay? So this is one view. Another view, the Madelung's view, is the one based on rho, J, and describing the quantum system as a quantum fluid. In all of these views, Bohm, de Broglie, or Madelung, we have the wave and we have the particle that moves like a cork. Well, in this regard, as you can see, there are no approximations at all. Therefore, we can put this representation or picture of quantum mechanics, okay, at the same level as Schrodinger's wave mechanics or Heisenberg's matrix theory or Dirac's interaction representation or Feynman's path integral representation. Feynman path integrals, by the way, found also a similar problem to Bohm. Okay, Feynman published his paper on path integrals 4 years before David Bohm, and when people saw that there were trajectories, that he was introducing trajectories in quantum mechanics, they were very reluctant to the results. Nowadays, it is a standard technique to compute quantum results, so it is well established too. We have the phase space representations of the Wigner-Moyal or the Husimi representation. So, added to this representation, we can also add without any problem, leaving aside all these ontological questions, the de Broglie, Madelung, Bohm, Takabayasi, because Takabayasi also worked this theory, representation. Now, how should we understand this, the quantum world from this perspective? Yes, as I said before, leaving aside ontology. Well, the point of view that I try to convey when I give a talk or when I talk to colleagues or in my research paper is that Bohmian particles are not real quantum particles. They are actually like tracer particles, no? The tracer particle that we can find in a classical fluid. For example, if we have a continuous medium, we can if you want to detect how the air evolves, we can just put there some dust particles, and they will tell us how, whether the flow is laminar or it is turbulent or whatever, as we can see here in these pictures. If we want to study, in this extreme case, the expansion of the universe, the tracer particles are galaxies, stars, and all these celestial bodies that separate one from the others. Okay. So, from this point of view, there is no real equivalence between a real particle, which is like the reality that we cannot access, and the particle that we describe with quantum mechanics. So, there are no, in this sense, hidden variables. Okay, the hidden variable that has been associated with Bohmian mechanics since its inception has been the position, the actual position of the particle. But if we cannot associate this position, these trajectories with the particle itself, with one electron or with one photon, then there is no point to talk about hidden variables. We could see them, as I said before, like these tracer particles, or for example, when we want to detect a magnetic field, what we do is to cast some iron dust around, and we immediately see that this iron dust distributes along the force lines formed by the field. This is the way how we know that this field exists. Well, there is actually a very beautiful experiment in quantum physics that reveals that the phase is actually a real element. Okay, this is the Aharonov-Bohm experiment that I'm sure you all have heard about. Okay, in this experiment, we shield the field, but still it has an important action on the electronic wave function. So again, there is an element that we cannot see, but that has an effect. If it has an effect, there is some sort of interaction. Therefore, the wave function is not simply a descriptive and a statistical descriptor of my system, as some people postulate, mainly in the area of quantum computation and quantum information. The wave function seems to have a real existence. What it is, we don't know, but at least we can study what is going on around. Well, here I can see some papers from the first experimental observation of the Aharonov-Bohm effect. We can see how, the field is shielded somewhere here, and we can see that how these interference fringes, they just move with respect to where they should appear. Now, where have these trajectories or similar trajectories been used before? Well, here we have Sommerfeld. He provided the analytical solutions for the metal plate, for the edges in metal plates. This was dating back to the 19th century. Well, here we can see in the intensity curves, and here phase curves. about 50 years later, more than 50 years later, right the same year that David Bohm published his paper, this Brombeck-Lokian published in Optic these nice streamlines. These streamlines correspond actually to streamlines associated with the electromagnetic field. There is no problem in computing this trajectory, except for the fact that we are dealing with a wave phenomenon. Okay, as you know, in optics, either we talk about rays or we talk about waves. Rays are somehow the short wavelength limit, or they appear in the short wavelength limit of waves. Okay. However, here we have rays that are not associated with this short wavelength limit. Well, in the later on, 20 years later, Prosser published a paper, with the same, using the same idea, published a paper where he found the trajectories in the case of the double slit problem. And they have this very interesting shape. Okay, here we have the surfaces of constant phase. Okay, this will be the Huygens waveforms, and we can see that these trajectories are sort of perpendicular to every point to these wavefronts. Later on, well, that's same here actually. In the realm of quantum chemistry, okay, Joe Hirschfelder introduced this idea. He published with his collaborators 4 nice papers about trajectories or streamlines in different problems associated with of interest in quantum chemistry, as it is for example, in this case, the penetration of barriers. And look at this, what he remarked is that this analysis is far-reaching. He already pointed that this kind of analysis could provide us with some clues on quantum systems that go beyond what we actually know, but by simply computing expectation values. A similar idea has been exploited since long ago, okay, in fluid dynamics, okay, chemical physics, I said, in the molecular physics. In this case, these trajectories are associated with magnetic fluxes, quantum magnetic fluxes. Okay, so by looking at this picture, we can see that this has been a kind of a explosion, okay, of this idea of exploring trajectories or Bohmian mechanics to understand in a deeper sense quantum problems, or at least not in a deeper sense, at least in an alternative manner. We can see that from these seminal works, okay, here in between the 70s, in the 70s and 80s, there are mainly works developed by the people, the collaborators of David Bohm. David Bohm, Kirsch Basil Haley, who passed away a few weeks ago, unfortunately. Okay, Peter Holland. But from the 90s on, we can see that there is a very important push to these works. This was because other people like Bob Wyatt, I introduced in a previous slide, all these people started to develop these Bohmian ideas in a more practical manner. That is, they said, okay, let's take this and let's see if we can either get new physics from them, okay, in our interpretations of molecular systems, or we can get new numerical tools. And the thing is that both work pretty well. Now, let's see what Bohmian mechanics, not that we have seen, just the general landscape. Let's see what Bohmian mechanics can tell us about different phenomena. Well, why should we be interested in this kind of Bohmian stuff? Well, let's say, let's think of a real lab. Okay, in a real lab, we have that things take place in a real place, in a real time. They are here, okay, and they move from here to here. So that's the point. There is nothing like an abstract entity that can be or cannot be. Okay, things are there. The quantum observables are statistical outcomes. Okay, this is undeniable. The quantum observable is not a mathematical object, but it is just a reality. It comes from statistics. When we have an electronic jump, it is not a single jump. It is something that we obtain for many electrons coming from one energy level to another energy level in an atom or in a molecule. And moreover, we assume that there are no event time correlation. That is, if we perform an experiment of diffraction with electrons, we assume that all those electrons involved in this experiment are not correlated, because otherwise we would not observe these nice diffraction patterns. So they behave as one, as an isolated particle. So let's see if we can reproduce these real lab experiments with numerical experiments based on these similar ideas. Let's consider a working tool for that. The working tool cannot be a standard quantum mechanics, in the sense that we are going to get general properties, because we have wave functions, standard wave functions. We want to have this view of event to reproduce the results event by event. And now, the phenomenon that is really important here is coherence. Okay, if there is no coherence, there is no point to use point mechanics. We can use classical mechanics as well. Okay, so because of this, my opinion is that, well, we have three nice features of this theory. First, it is rather intuitive, even if there was this extra term in the quantum Hamilton-Jacobi equation. Still, we have this classical-like view of quantum phenomena. It is 100% compatible with any other quantum theory, because in the end we have seen that Bohr mechanics is just quantum theory, it's nothing different from it. Okay, it's another view of the same. So, and it stresses the role of the quantum flux. This is very important because other views stress other properties. Okay, but Bohr mechanics particularly focuses on the role of quantum fluxes. Okay, and moreover provides us with a very particular view, or at a local level, of how these fluxes evolve. We can have a sort of global view in terms of the wave itself, but we can also have a specific view of how each point in this flow, in this wave, is moving. Okay, this is very important, as we are going to see. Well, let's go first to Young's experiment. We have here the wave function. This is a standard superposition. We can recast both partial waves, psi1 and psi2, in terms of density and phase. We introduce this. We compute rho with this. We compute j. Okay. We obtain these expressions, and now from them we obtain the equation of motion for trajectories, from which we are going to obtain the trajectories, which is this r dot here. Antisymmetric. This antisymmetric term is going to tell us that there is a rule that must always be preserved. Bohr mechanics shows us that through a given point in space, there cannot be two trajectories crossing it at the same time. Density of the central maximum is 4 times, as we expect, the intensity of each one of these two Gaussians separately. One could, appealing to from a mathematical point of view, to the superposition principle, we would say, well, we can get exactly the same if we run one Gaussian, we run the other, and we make the superposition. Well, that's fine. But this is not correct from a physical point of view. Why? Because, as we see here, the phase associated to this distribution is not a superposition of anything. It is not a superposition of anything. It is a non-linear process. If we recast this in terms of the two new elements that appear in Bohm's theory, this last term in the Hamilton-Jacobi equation, the quantum Hamilton-Jacobi equation, this last term is commonly known as Bohm's potential or Bohm's quantum potential, or simply as quantum potential. We obtain something like this, something that starts here, like two parabolas. Then, as soon as the two Gaussians start merging, increases a lot, okay, and then it starts relaxing. And it relaxes in the form of valleys and canyons. The trajectories are going to, or the probability density is going to move or to evolve through these valleys or these plateaus, because it doesn't like to be just to show I think the connection was over.
Angel, can you hear us?
Let me see.
Can you hear us, Angel?
Yeah, I can hear. I can hear.
Have some instabilities with the internet connection. I hope that it is still being recorded.
Okay.
It is recorded.
Okay. Okay.
Okay. Can you share your screen? Perfect. We can continue from here.
Okay, so let's move ahead and let's see the consequences in terms of trajectory, because I have been talking about trajectories, but we have not seen them yet. Well, the trajectories are displayed here. Here in both panels, we have exactly the same trajectories. There are these black lines, okay, but the contour plot on top of which they are superimposed on the left represents the probability density, on the right the velocity field. Well, you can see that the Gaussians come in this direction. Okay, this is time. Coming in this direction only means that they evolve. Okay, they are not moving there, because we are focusing only on the transverse direction, on their spreading. So as soon as they start interfering, these trajectories that look like hyperbolas, they start to distort, to get distorted. And soon afterwards, they start to get channelized along these regions where we observe the plateaus in the quantum potential and the valleys in the velocity field, which we see here. okay? And we see that each beam or set of trajectories can be uniquely related to an interference maximum, n equal to 0, plus or minus 1, plus or minus 2, etc. Okay? Now, the fact that we can that the trajectories do not cross is very interesting, because it leads us to think whether this works, or one could interpret it in that way, as if we had an impenetrable barrier there. Well, let's see. Let's make this the toy model. Okay, this is a small barrier. Okay, here, this is with a oh, sorry, this is an infinite barrier here. There is a well with a given width, and here there is no potential. The potential is 0. Okay. If this idea works, this means that describing the problem of the collision with an impenetrable barrier, okay, that follows a well, should be equivalent to having this two Gaussian superposition. Okay, here we have represented how this x minimum, I mean the range of the well, and this potential and the depth of the potential here, V0, are in terms of time. Okay, how this should be in terms of time. Well, we make the simulations. This is how. I mean, I mean, we are just putting the barrier here, the infinite barrier here. So look, this is the pattern or the interference of the two Gaussians, and this is the pattern that we obtain when we study this collision, okay, this particle with the barrier collision. We observe that we have maxima with the same width at those corresponding to Young's experiment, but there is one that has half the width, which is this tiny one here. Why half the width? Because the central maximum, as you can see here, should belong part to one say one side and part to the other side. Also, we find that this is small. This is rather small compared to this high intensity here. Well, this is because I mean, this is a kind of toy model. We could refine this model in order to increase the intensity here. But increasing the intensity here, what does it mean physically? It simply means that we have a resonance. This half a width peak is just a resonance that we have generated inside the well. And this is what the trajectories show. All the beams have nearly the same size, same width, except this one, which is half the width. Okay, all these trajectories are channelized along, I mean, parallel or nearly parallel to the impenetrable wall, just in compliance with this dynamical width of this potential. Now, let's pass now to the case of entanglement. Okay. Now, in entanglement, we have we may like to make several questions. Okay. First, how the coupling affects the systems. Okay. Now, to understand in a better way, okay, in a deeper way, what this spooky action at a distance really means. And of course, if we have two entangled systems, you know that if we look at one of them, if we trace over the other, we lose some of those features that make this to have or to show distinctive coherence trait, like interference. So we're going to work with a continuous variable system, just Gaussians. For an isolated system, our wave function is of this kind. If we have an entangled system, it is going to be of this kind. So we have two Gaussians, one for the degree of freedom x, the other for the degree of freedom y, one in position A and y in position B, or just the opposite, x in B and y in A. Okay, all of this is in one dimension for each subsystem, x and y. Okay, the very first thing that we observe is the following. This is without entangling anything yet. We can see that if we have a single Gaussian, it spreads like hyperbolas. This is something we saw before. Here below there is the contour plot of the density, probability density, and here below the probability field of the velocity. These rings here are just numerical errors. So it should be red, but the thing is the values are so high that the accuracy of the program didn't allow me to get the good representation. Okay. Now, if we make some transverse cut here, okay, we can see that this velocity increases linearly from negative positions to positive positions. Okay, at t equals 0.5, we have this inclination. Okay, and then as time passes by, the inclination gets relaxed. This is what makes the trajectories to be moving along essentially straight lines, okay? Straight trajectories. Now we go to two athletes. This is what we have seen before. But look, we commented that the superposition principle is good mathematically, but it is not that good from a physical point of view. Why? Because if we want to compute these velocity fields, they are not the superposition of one velocity field plus another velocity field. Remember that there was one velocity field plus other velocity field plus an interference plus some antisymmetry term. And we can see this through these transverse cuts, exactly the same as here. If we are in this region, in the regions where the Gaussians are not seeing each other yet, we have something like a straight line for the velocity. It goes down very fast, and then the straight line for the other Gaussian. We can see that at x equals 0, there is a break, very abrupt break between both. Okay, but still they both look pretty much like what we had before. As time passes by, the inclination of these lines decreases, but we start observing the appearance of these wiggles here. Okay, these wiggles indicate that they are going to make trajectories or to deflux to move towards the regions of local minima or maxima, I mean these stable ones, and to avoid those where we observe these spikes. Well, this is for just a single particle in a superposition or just in a single Gaussian. Let's see what happens when we compute these for two particles, x and y. This is here we have the horizontal axis is for x, the vertical axis is for y. Here we have a superposition for x and a single Gaussian for y. You can see that everything spreads, but here along the x direction we have interferences. Along the y direction we just have a single Gaussian. This Gaussian will be larger or shorter depending on whether we are in the maximum or in the minimum along the x direction. Now we go to both x described by superposition, y described by another superposition. This is still a factorizable state, okay? Well, now we have four Gaussians. They start increasing in size, and at some point, they give rise to this kind of chess-like pattern, okay, with many any local maximum around. Same as before, same as the top case. If we look along the y direction, we are going to observe an interference pattern that is going to be higher or shorter depending on whether along the x direction we are in a maximum or in a minimum. Now we go to the entangled state. Entangled state is like having this double two Gaussian superposition, but removing these diagonal elements here. So we will have these two elements. And what happens is that, well, something similar to what we observe in this figure emerges, in this figure for a Gaussian in the superposition, but along a diagonal. This is very interesting because this is actually the essence of entanglement. We haven't lost any coherence. The coherence is there. You can see it, but we have some fascinating behaviors. Let's put initial conditions. These are initial conditions for trajectories. Well, and this is what we observe. While we have a regular pattern in the first two cases, in the factorizable cases, we have something really, really weird, really odd when we look at the unentangled case. It seems that the particles are doing very weird things. Still, they must respect the non-crossing rule in this two-dimensional expanded space, but they are allowed in their subspaces to cross through the same point at the same time. Let's see it. Well, sorry. First, let's see what happens with the velocities. Well, this is the velocity along the x direction. Okay, you can see that for the factorizable states, we have near essentially the same in all cases. Okay, it doesn't matter whether we are at some value of I or another. We have exactly the same. However, when we go to the entangled state, we have this weird shape. This weird shape doesn't allow us to reinterpret this as a superposition of two things. Okay, we have something similar to what we observed already with the two slit, but this time in this expanded space. Well, it is because of this weird behavior that the particles, they interpreted as these conditions, they start moving and they start to accommodate along these stripes, these diagonal stripes. We can do exactly the same, but for the y component, the velocity. For the Gaussian with superposition, or for the double superposition, we have a similar behavior, but for the entangled state, we have again this kind of shapes. Let me introduce here the trajectory, how they look like. Here we have the projection along the x direction, here along the y direction, and you can see that this projection, the trajectories never crossed. Even if here in the three-dimensional representation, they look as if it was the case. If we have the superpositions, the two superpositions in the x and y, if we come to the x subspace or the y subspace, we have that they don't they don't mix, they don't cross at all. Okay, even if they look kind of weird. If we go to the entangled state, things change very dramatically, because as you can see in the x subspace or the y subspace, there is this mixture of trajectories. So it is not that the non-crossing rule is not being respected. It is only that the non-crossing rule only holds in the big space where coherence still exists. Here I present some models made with trajectories obtained from the corresponding density matrix. if we have a same density matrix describing a subsystem, the trajectories are never going to cross. This is kind of challenging because we have seen that with the entangled state, they were actually crossing. No? Well, what happens is that because we are keeping information from both slits, okay, the corresponding Bohmian trajectory is going to reintroduce this non-crossing rule, although we have lost all coherence. How do we know that we have lost all coherence? Because we don't observe interference fringes. We simply observe that they go very, very smoothly. So there's a kind of coherence associated with phases, and there is another coherence associated with with the fact that we keep information from where we started. How can we destroy this coherence? Well, by annihilating the information that comes either from the presence of one of the slits or from the presence of the other slit. This is what we show with another model. These models, okay, this information from one slit or from the other on the trajectories coming from the opposite slit is gradually suppressed, okay? And this corresponds precisely what we have just seen with the full or exact model. Now, let's just to finish, let me see how much time we have, okay? Let's see what I call as post-Bohmian mechanics. Feynman said that same equations have the same solutions. So if this is true, why not extending these ideas, these Bohmian ideas, to other fields of research? After all, this is what we have seen with the example that I showed before in chemical physics, with sound waves, with light, etc. So I'm going to present some recent results. Well, here we have a Schrodinger's equation. Okay, we got the equation of motion. Now, if we substitute the time, okay, by z, by the coordinate along which we propagate light, okay, we can obtain, well, the paraxial Helmholtz equation for which we can define sort of effective velocity field. It is not a velocity field as such, because a proper velocity field, because there is no time, there is only evolution along this z coordinate. But still, it serves as an effective time. So in general, we can talk about effective transverse velocity fields. Okay. Well, with this, we have recently described, for example, the degradation of AD beams, as formerly introduced by Berry and Ballas by the end of the 70s, that were later on in the 2007 created or generated experimentally with light. Okay, here in these panels, there are outcomes from the experiment, and this is our simulation. But here we have the trajectories. Here we can see if we then have this finiteness in the energy, which means taking the AD beam, this tail, and extending to infinity, okay, we would have parabolas, true parabolas. However, the effect of cutting with an exponential truncating this tail, this long tail, makes that the energy can escape little by little, gradually, out backwards from the main beam. Well, these results actually corresponds very nicely with the numerical, with the experimental data obtained by Sibyl and Christodoulides in 2007. Okay. We extended this idea also more recently to the case of incoherent light or partially coherent light. Partially coherent light is described by descriptors which are analogous to the density matrix in quantum mechanics. In this case, they are called, it is called the cross-spectral density. If we assume that the realizations of the field of my optical field are of this kind, okay, I average over these realizations, and I obtain my cross-spectral density. So I can formally prove that the evolution of these averages satisfies this continuity equation, and therefore we can define, well, we define the intensity this way, but also a sort of average current in this other way, which looks pretty much like the quantum flux that we have in standard quantum mechanics. So if we apply this to partially coherent eddy beams, okay, let me skip these questions. We obtain this effective velocity field, which looks weird, but that renders this kind of behavior. Here we have something with little coherence, okay, very poor coherence. We don't observe the oscillations typical of an eddy beam, but very, very extended in tail. This is with a very high energy content. We can see that regardless of these wiggles, these interferences, all the trajectories which select just a set of them, just within certain conditions in this rear part, most of them, mostly they move along parabolic trajectories. So we can say that the fact that an eddy beam doesn't change in shape as it propagates, as suggested or as proved by Berry, has nothing to do with the coherence of the beam. It is a property that has to do with the energy of the beam. There's a kind of push coming from this infinite tail, just making that all the trajectories necessarily they must move forward. They cannot move backwards. If we introduce the cut, but the beam is highly coherent, okay, there are these interference traits there, these oscillations, we can see that effectively the effect of truncating this infinite tail, this infinite energy content, provokes that the trajectories will try to escape little by little. Okay, we can have something intermediate where we can see that, of course, this is the case. We have poor coherence, and the trajectories still go backwards. Yet we can show that interference traits can still be generated. This is the case of poor coherence. We have two contra-propagating eddy beams. Okay, they approach, and when as soon as they overlap and they pass each other, or this is how we would describe this mathematically, a series of interference fringes or maxima start appearing. So we are somehow recovering this nice feature. Here to the right, we have a transverse cut of the velocity field. You can see how from something flat at the beginning we have these inclined lines, but as soon as the maxima, the leading maxima, pass the intermediate position, we start generating here something in between that little by little is going to be showing these oscillations. Well, here there is another case where we can see again that independently of this structure, in the middle position, once the two leading maxima has overcome the central position, there are some nice interference features. And the same if we have a short spatial extension poor coherence. So just to finish, well, we can see that quantum dynamics are essentially ruled at the local level by the quantum phase. This is very important because we typically pay attention in quantum mechanics to observables. However, However, we can see that the phase, and in particular the velocity field that it generates, is even more relevant. Now, the probability density with this picture, with this Bohmian picture, can be understood as an effect of the propagation of these phases. If we have non-correlated systems, okay, the coherence transfer between particles taken in such a way that the velocity field that acts on each particle do not influence one another. Okay, we have one system, two, or infinite system. We don't care. The fact is each one is going to be truly independent on the other. You may think, well, but this is obvious in a way. Well, it is obvious from a mathematical point of view, but we have seen that not always mathematics and physics have a clear correspondence. When we have entangled systems, things change very dramatically because everything gets very, very, very messy. And this makes that when we observe one system or the other, what happens to the system that we are observing is strongly dependent on the other at a dynamical way. And this is precisely what is going to rule the properties that we find in entangled states. The coherence is nothing but an effect of entanglement, okay? Of this high correlation, of this fact that we cannot disclose the systems because their velocities are quite intertwined. And now, what does it mean that the system become classical? Does it make any sense? Well, at least from this point of view, it doesn't make too much sense. What we have are systems that, when we look at their specific subspace, they have lost some properties. But the quantumness is still there because it is in the big system that still exists. And just finally, well, we can see that these ideas are not proper of quantum mechanics itself. They can be extended with very fruitful benefits to other areas of physics. Okay, if we are thinking of quantum mechanics as something that describes some hidden variables and blah blah blah, the only thing that we get is to put this in the end of the day in a box. However, if we think of quantum mechanics as an effective tool, as an effective way to recast quantum theories and general wave phenomena, we can extend it to any problem that we may have in mind. And with this, well, thank you very much for your attention.
Thank you, Angel. Questions from the audience? May I ask some questions? Okay. From the last part, okay, I do not know many things about optics from the airy beams, okay? So as far as I know, they are special type of solutions of the wave of the Schrödinger's wave equation that they have the ability to preserve their form.
Yes.
And they're even in the free space, and that in the free space they follow curved trajectories. Am I correct?
Yeah.
So what I understand is that you take the Bohmian formalism and you try to make to extract some similar kind of equations that help you in the field of optics.
Yes.
Oh, okay. One is that this is linear optics. Am I correct?
Yes. It is totally.
From a non-linear parameter or from non-linear contribution. This is just the usual Schrödinger equation.
Yes, it is the linear Schrödinger equation. You ask for a solution that is not spreading, not diffusing with time, and well, you get it.
As far as I know, Angel, the airy beams are used in the field of fiber optics
Yes,
in order to pass the signal without environmental noise,
yes,
because they have the ability to regenerate themselves
yes,
fighting
yes,
an obstacle.
yes.
Okay, perfect. Something else. You say you are talking about the decoherence. So I've lost you maybe because of the connection. You were talking about the double slit experiment, and then you talked about decoherence, and I've lost you. You took the density matrix of the wave function, okay,
Yes.
and then you traced out the one of the two variables.
Yes.
So you were with the reduced density matrix.
With the reduced, I mean, you can do the following. You can study the two-slit experiment just with two particles,
Yeah, yes.
and then you immediately see what is going on there. Or you can determine the trajectories from the reduced density matrix. And if you do so, if you use the reduced density matrix, the problem is that all the interference terms there disappear. I mean, those that carry some information about the phases disappear, but those containing information that both slits were open at the same time at the beginning still remain. So this information is what tells the trajectories that they cannot cross each other. So this is why I mentioned that there is this sort of extra or new concept of coherence, a coherence based on information, not on phases, on phase correlation.
Yes.
So if you want to destroy that,
So the reduced density matrix, what you see there, it's not classical.
yeah,
After tracing out the second degree of
it's
freedom.
not classical. I mean,
Information from the original setup.
no, wait. It is not that the reduced density matrix is not classical. It is that the trajectories are not classical.
Yeah.
Because remember that the trajectories, the equation of motion for the trajectories is just the flux divided by the probability density. So both the flux and the probability density are obtained from the density matrix. So even if they look like classical, each of them separately, when you put them together into the equation of motion for the trajectories, this is not classical anymore.
Okay.
Because for J, you have that J is equal to J1 plus J2. That's fine. For rho, you have that rho is equal to rho1 and rho2. However, you cannot recast V as V1 plus V2 or V1 and V2 separate.
The equation of motion for the reduced system, after tracing out the second degree of freedom, it is still of Bohmian type.
Yes.
With something else.
Yes.
Okay. Okay. Anyway. Okay.
Maybe I should have included the equations there.
Yes. Okay. I will say it later. Thank you very much. We are going to upload this talk on the channel of the Academy. So goodbye from Athens.
So thank you very much to you and to everyone there in the audience.
Thank you very much.
I hope to coincide with you soon again.
Okay, I will send you the link and I will talk to you later, Angel. Okay?
Okay.
Thank you very much again.
Bye.
Bye bye.
Πάμε εδώ.